In this video, I'll explain what the central limit theorem is and how it's used in statistics. Suppose you are designing elevators. Each elevator has a counterweight to balance the weight of the elevator car and the occupants. So one thing you might want to know is, in a group of 5 people, what is their average per person weight? To investigate this, you download some data from the National Health and Nutrition Examination Survey, which is conducted by the Centers for Disease Control and Prevention. They get a nationally representative sample of people and measure, among other things, their weight. So here is a histogram of the weights of the people in the sample. This distribution has a mean of 65.14 kilograms and a standard deviation of 32.89 kilograms. However, the distribution is bimodal and highly skewed to the right. So what would a sampling distribution of 5-person average weights look like? Pause the video and make a prediction. Now let's set up a simulation. So we'll use this distribution of individual weights as a model. We'll sample 5 people at a time and take the mean of their weight. Then we'll repeat this many times. Here we'll do 1,000 samples. And then we can look at the sampling distribution of these 5-person averages. And this sampling distribution is unimodal and symmetric, even though the original distribution of weights was neither unimodal nor symmetric. Now, what if we had looked at 10-person samples and took the mean weight? What do you think the sampling distribution would have looked like? Let's simulate this. So we'll use the same model, but we'll sample 10 people at a time and take the mean of their weight. Then repeat this many times. And then we can look at the sampling distribution of these 10-person averages. And this sampling distribution is unimodal and symmetric. Now, what if we had looked at 20-person samples and took the mean weight? What do you think the sampling distribution would have looked like? Let's simulate this. So we'll use this same model, but we'll sample 20 people at a time and take the mean of their weight. Then repeat this many times. And then we can look at the sampling distribution of these 20-person averages. And this sampling distribution is unimodal and symmetric, and appears to have relatively little variation. Let's take a look at all of the distributions we've generated. So we had our distribution of individual weights, our 20-person average weights, our 10-person average weights, and our 5-person average weights. And we can compare the shape, center, and spread of these distributions. For the individual weights, the distribution is bimodal and skewed to the right. In contrast, the 3 sampling distributions are all unimodal and symmetric. The distribution of individual weights has a mean of 65.14 kilograms, and the 3 sampling distributions have mean weights of 65.39, 65.16, and 65.02 kilograms, all very close to each other. Finally, the standard deviation for the individual weights is 32.89 kilograms. For the sampling distribution of 5-person means, it's 14.61 kilograms. For the 10-person means, it's 10.42 kilograms. And for the 20-person averages, it's 7.32 kilograms. So as we increase the sample size, the sampling distributions become unimodal and symmetric, and have less variation, but they're all centered around the same mean. So why is this happening? Let's take a look at the distribution of individual weights. So if we randomly select 5 individual weights from this distribution, we might get one from the tail or one from the lower half, but most of them are likely to come from near the central mode. So their average weight would be not too far from the overall population average. And the same would be true of other 5-person samples. And this would give us the resulting sampling distribution, where most of the 5-person averages are relatively close to the overall population average. Now, what if we had used 10-person samples instead of 5-person samples? If we randomly selected 10 individual weights from this distribution, we might get one from the tail or one from the lower half, but most of them are likely to come from near the central mode. And since there are 10 instead of 5, the weights from near the central node are more likely to balance out the occasional weight from the tail. So this would make each of these 10-person averages tend to be even closer to the overall population average, and make the resulting distribution have even less variation. Now, let's go back and compare those four distributions. So we've thought about why using a larger sample size makes the resulting sampling distribution have less variation, and why the averages tend to be clustered around the overall population mean. And it turns out that we can make this pattern more exact. Not only do the shapes of the sampling distributions become unimodal and symmetric, but they approach the shape of a normal distribution, which is sometimes called a bell curve. The center of each sampling distribution will be the overall population average, and the standard deviation of each sampling distribution can be calculated by taking the population standard deviation, which we can approximate using the sample standard deviation, and dividing by the square root of the sample size, by the square root of 5, or 10, or 20. And there is an underlying theoretical reason for this pattern. The central limit theorem states that if a population has a mean of mu and a standard deviation of sigma, and you take n independent observations to create a sampling distribution of sample means, then the sampling distribution will have a mean of mu, a standard deviation of sigma divided by the square root of n, and will tend to follow a normal distribution as n increases. So the sampling distributions we've looked at can often be approximated by a normal distribution. So this means we can often use normal distributions to compute p-values and construct interval estimates. And this central limit theorem is the reason why the normal distribution plays such a large role in statistics.